Hello again, and thank you. And here is the remote. Okay, basically, this talk is about the things that we saw about Redis 4.2, but from the point of view of how they actually work inside. Because certain features required to create completely new data structures, to change the internals in a significant way in order to be implemented. The first thing that was needed was an implementation of the Redis tree. I don't know if you know what a Redis tree is, but that's basically a picture of the Redis tree. In this moment, it's smiling. You can see that. Basically, it's a tri-data structure where each node can have multiple children depending on the next character. And as you can see, this kind of trees will compress the common prefixes. So it's a very memory efficient way to store a dictionary of things. Why this was needed? Redis cluster needs to track in what hash slot a key belongs. If there is an hashing, and then the Redis cluster key space is split among multiple hash slots. To perform this tracking, I used to use internally a sorted set, just hidden from the outside in order to do this. But eventually we discovered that loading an RDB file for Redis cluster took like 5 times compared to loading the same RDB file of a vanilla instance without clustering. And that was because when the keys were created, to update the sorted set was very slow compared to what we needed. So I started to look for a new data structure in order to take a dictionary of keys and hash slots mappings. At the same time, my colleague Dvir was working at the Redis search module. And he also was exploring the same kind of problems to create a fast inverted index for his own needs. And he said to me, you know, probably you should try to use a Redis tree as well. I'm using a Redis tree. And we start basically this game where I wrote my implementation. He was writing his implementation of the Redis tree, and we started to make a speed race. I can make it faster. No, you can make it faster. And but of course, every time we share the ideas in order to make it faster. And in the end, basically, the Redis tree that we obtained is a lot faster compared to the Redis, even the Redis hash tables. It's like 3 times faster or something like that. This is why it works well and it's fast. This is the structure of one node in the racks. I call it my library racks. Basically, there is an header where there is information about the node, like how many children and stuff like that. But the interesting thing is that the children that this node has are unknowns inside the node itself. So you don't have to walk pointers in order to understand what the children contain, okay? It's basically the letter that comes in the next node is stored at the edge, not at the next node. It means that when you want to scan, you are inside the same cache line of the CPU, and it's very fast. And the pointers instead are to the elements that are unknowns are stored contiguously. It means that when you add or remove elements, you have to do a few mem moves. But the mem moves turn out to be extremely fast when everything is in cache. So it works basically very well. Then there is a value pointer. As you can see in the picture, you can store, of course, a satellite information in the value pointer. However, certain dictionaries don't have a value. It's just, for example, as Redis set, has no associated value. So there is a reserved bit inside the node header where you see I have an information about an associated pointer or not. And when you have not, you don't allocate the space. So it's very efficient in order to store things that are not linked to external values. The implementation is a bit complex because Redis trees are quite a complex data structure. When you remove a node, you have to recompress stuff and so forth. It's a bit complex. So it's more than twice the size of Dict, the hash table implementation of Redis. But uses less memory, it's way faster, and because it's a sorted set of keys, you can iterate the keys in a much better way compared to what you can do with a hash table. In order to test racks, because the implementation of the Redis trees is so complex, it's very easy to make mistakes. I used a particular way of testing it, consisting only of fuzz testing, and every time I found, I started writing unit tests. Every time I found a bug in the unit test, I modified the fuzzer in order to find independently that bug. And with this iterative process, I arrived at the first fuzzer. Then I used gcov in order to check the coverage of the source code used with the fuzzer. And I modified the fuzzer in order to cover all the lines of code with the fuzzer. Once I did that and I left it running for some time, it found also other bugs. And in the end, I could modify the fuzzer and add more and more and more data model use cases, and he was not able to find any bug. And when I applied, replaced basically inside Redis cluster the sorted set with racks, everything worked immediately. All the units were passing the first time, because this fuzz process helped a lot in order to provide a kind of bug-free implementation. Maybe there is some bug left, but I think that I explored the most corner cases of the implementation. This is going to be used in a lot of places. It started as a cluster speed regression fixing, but it's the basic data structure for the streams. It's the Redis tree that indexes the pieces of which streams are composed of. And it will be used in order to represent hashes and sets instead of hash tables, because it's not just that it's more memory efficient and faster, but also the problem with the hash tables is that when you reach a given level of saturation of the hash table, you have to perform a rehashing. And the rehashing cannot block Redis, so it's performed in an incremental fashion. And this burns the CPU in the background, so it's just better to use the Redis tree. There is one very cool thing also. Do you know, currently Redis uses double encoding. It means, for example, if a hash is small, it's encoded as a blob of values. If a given size is rigid, it's promoted to a full hash table. This design has a problem, that basically after a given number of elements, the memory efficiency goes extremely low. Instead, using the Redis tree, where the leaves of the Redis tree are this kind of blobs used currently in the small encoding, I can have a single encoding that's always a Redis tree of blobs, and this scales in the small hashes and scales in the big hashes. So it's going to probably something like lists will happen, that the memory usage of big sets and hashes will drop to 10% of what it's today. And 10% is one order of magnitude. It means that's the difference between being able to apply Redis for certain use cases or not. So it's cool. The second thing is the Listpack. Okay, that's the story of the Listpacks. Before the Listpacks, we currently are using a data structure that's called Ziplists. It's a very simple data structure. Basically, you want to store a set of elements, and you want to store them so that they are very, very space efficient. What you do is to allocate a bunch of memory, use a separator with some kind of encoding, like message back, and you store one and the other and the other and the other and the other. Okay, it's very simple. However, in our data structure, we needed a peculiar feature. You have to be able to scan elements also in the reverse order, because they are used in order to encode lists. So if I have this blob, I want to be able also to read it from right to left in the contrary fashion. Why? Because if I have a list encoded in that way and I want the last element, I don't want to scan everything, reach the last element and output it to the user. I want to start from the tail and parse it. For some reason recently, we started to receive a few bug reports about crashes inside Redis. Most crashes inside Redis are faulty memory modules or cosmic rays or something like that, completely not reproducible. Even when you look at the registers, you see like, I don't know, odd pointers or stuff that's not possible. But sometimes it's bugs actually. And we could really not live with the idea that Ziplist was bugged. It was contributed many years ago from a very good programmer called Peter Nordhaus that created many things inside Redis, improved a lot the sorted set implementations, and during the process it also contributed that. And it looked very strange that after many years it was running stable, but now it looked like it was unstable. The reality is that basically when there are corruptions, they tend to show up where there are many encoded things and pointers. If you are caching HTML fragments and they corrupt a random byte in your memory of your system, you probably are going to corrupt, for example, one character inside the HTML. And you never notice that because, okay, one R will be a T in a random HTML document, but it's very hard to detect. Instead, imagine if your memory is packed of pointers and encoded things and the prefixed lengths, one bit and everything crashes. So it's just that people were using a lot Listpacks, and we saw these corruptions in that part of the code. However, we were not satisfied with that, so we started a huge debugging activity with 3 programmers working day and night to check a bug where there was probably none. And we looked so strongly at it that eventually I found a bug. Reading the source code again, I found a bug that I could reproduce with a sequence of Redis commands. However, the crashes were in the hash data type, and I found a bug that could only apply to the list data type. So it was a bug, but it was not what I was looking for. But basically, all this process we learned something from this process. We learned that the Listpack implementation was way too complex even to read and to analyze. And that's why. The main problem when you have to read the things from right to left is that you have to find a suitable encoding in order to read bytes in the reverse order. This is what Ziplists were using. They basically, instead of encoding a single entry, Ziplist encoded the previous length and then the entry. The length of the previous entry and then the entry. This way, if you have a pointer to the prevlen field of the last entry, you can scan backward, jumping to the left, okay? There is a problem with that. Most entries are very small. So normally it uses a double encoding. The prevlen could be represented by a single byte or by 5 bytes. But with an encoding like that, sometimes if you change an element, the previous encoding length changes in a way that you no longer can represent it with a single byte, and you promote it to 5 bytes, and there is a cascading effect where you have to update everything. This made the code extremely hard to follow and to understand. So I was looking to design a new version to replace Ziplists. And this is how list packs were created. One of my colleagues in Tel Aviv, Yuval, had an idea. What about storing the entry len after the entry itself so that it remains local? We basically store not the previous entry length, but this entry length at the right. However, how do you read something stored at the right, from the right to the left? And he invented this very smart encoding. Basically, you start from the right. As long as the most significant bit is set to 1, it means there are other bytes to read. When at least at the end it's set to 0, it means there is nothing more to read. So this is a very smart encoding because it's variable length size. Small entries will use little memory, bigger entry more memory, and it's perfectly in order to scan from right to left. Moreover, now the entry has only local informations, so you can glue and split list packs and everything will be consistent. And so this is the list pack format. It's cool because we have like an RFC. We created a full documentation before starting to code, and then I implemented it a few days ago before leaving for San Francisco, but still it's a work in progress. It's 1/3 of the source code of Ziplists, even if it's faster, does more, but the complexity reduction because of the new encoding is much better. Also, I totally changed the internal encoding in order to be more suitable for Redis use cases. Do you know message pack and stuff like that? They try to encode a lot of information in little space. However, how do you pick the information that you can encode with small bytes, and how do you pick the ones that are more wasteful? Depends on the model you have in mind. What's going to be more frequent, a small string or a small number, and stuff like that. List packs are implemented in order to store efficiently the kind of data that normally Redis users put inside Redis instances, like small positive integers can be represented with a single byte and stuff like that. And it's a lot less, it's not designed in order to represent like list packs, it was like message pack doubles or stuff like that, because in Redis everything is a string, so we specialize it much more compared to the encodings available as well. Let's talk about thread safe context. So the big news is that you can have things like keys running in the background together with the Redis main thread without bad things happening. So you can implement in modules slow commands that actually run in a parallel way with the rest of the main thread and don't block anything. However, how this was obtained? It started by implementing an API in order to block and unblock a client from a module. So like the blocking list commands, but for modules. At some point you get the handle of the client and you say, I want to block this client. Then you could spawn a thread, do some work like an HTTP request to an external server, and when the data is available, you return it to the client, unblocking the client. Since the first version of this API, you could call the Redis module unblock client API from within a thread. However, what you could not do is to call the other Redis module API calls from the thread, like give me the set length, add this element to a sorted set. It was not possible to call this from the thread because the Redis main thread was accessing at the same time to the same data structure, so there was a race condition. However, this is how the Redis main thread event loop works. You are inside the event loop, you call like the hepool system call or select or whatever you want for multiplexing, and then when you receive the list of clients that are ready to be writable or readable, you send buffers, read the protocol, dispatch the commands, do whatever you want. Basically, when you are inside the event loop, nobody is touching the data structures of Redis. When you are instead in the processing command stage that you are dispatching the commands, then it's the critical section. This is what we did. Basically, the modules use a global interpreter lock to understand when it's safe to call Redis commands from other threads. When we enter the event loop and Redis is not accessing the critical section, that's a perfect moment to release the global interpreter lock so that modules can do work. Also, this is normally the multiplexing API is very slow. And also sometimes it just waits, because when no client is ready to be processed, the kernel blocks there. When the kernel is blocked there, we have a lot of CPU time in order to run commands from the threads. When finally the event loop is ready to be returned, to return to the main thread so that commands are dispatched, we acquire again the global interpreter lock. And it works very well. For example, now I will show you the implementation of non-blocking version of the keys command. I will not show you the full implementation, but the interesting part. So basically you are inside the thread in this moment, and what you do is basically you want to lock the context. Basically this is where you acquire the global interpreter lock. At this point it's safe to call, for example, the scan command, and then you unlock the context. When you receive your reply is a safe object that can be accessed without any locking from the thread. So the contention is only limited to calling the Redis command, and then there is no longer contention. The problem is that we need to also be able to send replies to the client from the thread. And fortunately this can be done without having any locking. Why? Because the context creates, when I create a thread safe context, I create a fake client inside. The client is completely dumb. It's like a Redis client data structure. It's not really the client I want to send the reply to. The Redis reply buffer is a linked list of objects. The cool thing about linked lists is that I can relink them to another object in constant time. It's just a pointer. So when finally I unblock my client, I take the objects, the reply objects accumulating in my fake client, and I link them to the actual client that expects the replies. And thanks to this trick, what happens basically is that I can just have the contention when I call the Redis internals, and then the module is free to reply to the client or post-process the information it got from Redis, or even conduct another node via networking. It can do whatever it wants, really. However, this is not enough. It's great, but it's possible to do more from the point of view of the threading. One thing that is possible to do is that one module can say, I want to lock a key of Redis inside a thread. Once you get a key lock, you are able to operate on the value in any way you want, because all the other clients that want the same key in the main thread will be blocked and will wait. When you finally unlock the key, then the other requests can continue. It means basically that we can implement full parallelism as long as different clients are accessing different keys. One important thing is that this doesn't really apply to fast commands, like O1 or logarithmic commands are not sped up by all the outputs. They could run slower, because all the time of slow commands is actually wasted in read, write, protocol parsing and stuff like that. So this is part of the threading of Redis, but there is another story. That's threading the other part, the I/O, like Memcache does, and the protocol parsing. All the part that doesn't access the keys is also what we want to thread. And a few months ago, I wrote basically a proof of concept of that. I started with a thread that accepts the new connections. then this thread passes the clients to a pool of threads that implement each one implement an event loop. So we have multiple call to ePool or select or KQ, whatever. And it works surprisingly well because they have to basically hold a lock only when accessing the data structures, but otherwise everything is parallelized. It's a full of concepts, so after 2 minutes you play with it, it will crash in terrible ways, and because there are many things to synchronize. Now, that would be much simpler to implement if we could use C11 atomic data types. You know, the new version of C, of the C specification, one called the C11, has atomic data types as first citizen inside the language. It's great. Using them, it's much faster to write complex things because you don't need all these mutexes or you don't need to use the sing primitives or built-ins of GCC and stuff like that. However, it's probably this part will be postponed to Redis 5.0. I'm not sure. I will try to put it in 4.2, but I believe that key locking is the first thing to do, and then I/O threading is the next one. But, well, at this point, I mean, the path is traced, and sooner or later we will end with a completely threaded Redis implementation. And that's all. If you have any question on the implementation of the new things, I will be very happy to provide you any insight. Thank you. Thanks. Psst. Do you have any question? Yeah. Exactly. Good question. The I/O threading patch that I tried to write as a proof of concept is based on the idea that you configure the number of threads in the Redis configuration file. The threads are creating a start time and are those threads. From the point of view of threading the modules things, there is currently not this kind of limit because it's a long running request, so it's much more like an SQL database where you create one thread for every request. However, there must be a way so that Redis can say, no, don't use more than this number of threads. Currently we lack that, but it's very important because otherwise you end with an explosive number of, and the kernel scheduler will lose all the time trying to schedule things instead of do actual work. It's an open problem actually, but right now it's up to the module. So a given module can see, okay, I will limit the number of threads to this number, or I will do whatever else, but it's an open problem. Thank you. Yeah.
With the reimplementation of sorted sets, do you see the scores being able to allow strings instead of just floats?
Okay, basically, the Radix tree is not going, unfortunately, to replace the sorted sets. All the other data structures, yes, can be replaced by Radix trees, but not sorted sets for one reason. Because sorted sets are able to provide ranking. You can say, this element, what position it has, not just iterating, but you can say, like, what's the position of that? And Redis will reply, the rank of this element is 95. In order to do that, you need to have an augmented data structure where for every edge in the tree, you have the span, how many elements are covered under this element. And to put that in the Redis tree will be a problem. However, I think that what you are interested to do, you can do it already with the properties of Redis sorted sets to be, if you put all the same score in all the elements, then they are lexicographically ordered. You know that?
Yes.
But in order to associate a value, you have to pick a separator. So basically, if you want like a string map, where you order for score, for string, what you do is to put the first part that's the string you want to use as index, then a separator that's guaranteed to never occur in the string we are using to sort, and then the value. It's a bit of an hack, but it's impressive what you can do with that. There is have you ever read the indexing page we have at redis.io?
Yes.
Okay, so you know everything already. This is the maximum you can do right now.
Thank you.
You're welcome. Yeah.
Yes, as you say, so there is coming on with many features already, right? Right. So when you have the moment, it says no RedisConf API for Redis. In the coming releases, having more different capabilities, are we going to be able to handle the RedisConf API from Redis?
Yes, this is part of 4.0 already. This 4.0 was delayed because I really wanted to put that inside. So I implemented it a few weeks ago. Now from the thread you can call the context APIs, modules context APIs. So this is huge. I believe that we will see cool things about that because it means that for example, I can write a Redis module for 4.0 where common operations that like as union, set intersections, stuff like that are performed incrementally without blocking the server. And this opens very new opportunities. Thank you. Yeah. Absolutely. So basically, the problem with client-side caching is that it's very simple to take objects in memory, but it's not so simple, but you can implement a client that's smart enough. But then to invalidate things is a bit more complex. There are two ways. Either your clients are actually servers and they communicate. So if a client sets a new key and changes the value, it's going to stream this information to the other clients. So you are creating basically an infrastructure on top of Redis where the clients are very smart. Or you can use the server itself, a smarter version of the server that's the specific feature to invalidate your objects. For example, you connect to Redis and you send a command that put the connection in tracking mode, in client caching mode. Every command you send to the Redis server will be used Redis will extract the keys and will populate a Bloom filter to remember if a given key was ever asked or not in the context of this connection. What happens is that if the server sees a command that changes a given key, it checks all the clients that could be affected, that are the clients in caching mode that in the previous, in the past requested that key. And it sends an invalidation message. It tells the client, hey, maybe if you have this cached value still in memory, you should deprecate it because there is a new value. Or in the deprecation message there could be already the new value, potentially, in order to save round trips. Depends on the kind of value. For strings makes sense, for large values maybe not, I don't know. However, what happens in this way, if the Bloom filter pollutes, becomes more and more full of ones, and at some point it will match any string possible. What is the solution? One is to have multiple Bloom filters with time guarantees. Like I can say you that I will send invalidation messages for every key that you requested in the last 10 minutes. So what you do is in client side to remove everything that's older than 10 minutes. Okay, that's a possibility. Otherwise you don't use a Bloom filter, but you actually use Radix tree. That's a possibility as well. So you really remember what are the keys that the client is caching and not. There are different possibilities in order to understand. But Friday morning, there is a meeting open to everybody that want to attend such meeting, where we will cover Redis internal details, where we will shape together how we can implement that inside Redis, not just client-side caching, but other features I want to discuss with skilled people like you, and in order to check different models for Redis 4.2 implementations of stuff. And there will be breakfast from 8 to 9 o'clock, and then in 9 o'clock we will meet in a room that's called, sorry? Exactly, BNC something. It's over there. And if you want to join us, we can discuss how to. You can bring your use case. You can say why Redis for your use case sucks, and we can understand how to fix it. Or you can say what operation challenges you face, and we try to understand how to fix Redis in order to make it better. It's a like get real process in order where we stress not in the fact that Redis is cool, but in all the things that Redis does badly, where we can improve that, and I think it can be very interesting. The conferences are nice, but are information going from one person to the other exchanges. Friday, it won't be actually something where we say more actionable things, like we can do that and we can do that. For example, psync 2 originated from a day like that. So many important Redis features originate in this way. So I hope that some of you can join us to see. Also, we are very interested in client authors, in the library client authors. If you interact with Redis at protocol level and you want to say your point of view, that will be cool. There are other questions? Probably not. Thank you. Everything you want to talk with me, I will be at your disposal. Thanks.